GISP Unofficial Study Guide, Section 6, Analytical Methods. Section 601, Understanding of Data Selection Queries and Views. Attribute selection is selecting features based on filters of attributes. Types of attribute selection include new selection, add to selection, remove from selection, subset selection, switch selection, and clear selection. Spatial selection methods include intersect, within a distance, contains, which is when features contain an input polygon. The input polygon is selected. Completely contains, which is when features must be completely in an input polygon. The input polygon is selected. Contains Clementini. Features must be completely in the input polygon, but if it's on the boundary, it will not be selected. Within. Features will be selected if inside a selecting polygon. Completely within. Features will be selected if completely within selecting polygon, with no overlap. Within Clementini is when features will be selected and cannot be entirely on the boundary of the features. Are identical to. Features are identical to the input layer. Boundary touches. Features will be selected if they have a boundary that touches selecting features. They must be completely inside or outside the polygon. Share a line segment with is when features are selected if they share a line segment. Crossed by the outline of is when input features will be selected if they are crossed by the outline of a selecting feature. Have their center in. Features will be selected if their center falls within a selecting feature. Contained by is the same as within. Location selection. Selecting features within a certain distance of a location. Spatial data selection functions. Spatial data selection functions include join, combining two attribute tables into one using a common key between tables. Merge, combines multiple input datasets of the same data type into a single new output. Append, combines datasets of the same data type into an existing dataset. Union, combines input features with another feature dataset. Clip, extracts input features that overlay the clip features, and keeps inputs attributes. Intersect, extracts features which overlap in all layers to a new feature class, and joins the attribute tables. Section 602, Understanding of Techniques and Implications of Data Classification. Classification is grouping objects with similar symbols. Up to 7 classes are recommended, but sticking to 5 classes is better. Classes should be exhaustive, which means they describe all possible values, and should not overlap, which means no value can fall into 2 classes. Types of data classification include equal range, quantiles, standard deviation, natural breaks, and symbology. Data classification techniques are equal range, which means equal distance between class breaks, quantiles, which means an equal number of observations in each class, standard deviation makes the class breaks based on distance of standard deviation from the mean, natural breaks is when the class breaks conform to gaps in data distribution. Symbology is when one layer can be symbolized by an attribute. The implications of using different classification styles is that each will highlight different aspects of the trends of the dataset. Choosing the wrong classification methodology could cause the data to hide important information or misinform the reader. Classification is the process of sorting or arranging entities into groups or categories. On a map, the process of representing members of a group by the same symbol, usually defined in a legend. Classification is used in GIS, cartography, and remote sensing to generalize complexity in and extract meaning from geographic phenomena and geospatial data. There are different kinds of classifications, but all will generally involve a classification schema or key, which is a set of criteria, usually based on the attributes of the individuals, for deciding which individuals go into each class. Changing the classification of a dataset can create a variety of different maps. Data classification. The process of data classification combines raw data into predefined classes or bins. These classes may be represented in a map by some unique symbols, or, in the case of choropleth maps, by a unique color or hue. Choropleth maps are thematic maps shaded with graduated colors to represent some statistical variable of interest. Equal interval or equal step classification method divides the range of attribute values into equally sized classes. Quantile breaks. The quantile classification method produces equal numbers of observations into each class. This method is best for data that is evenly distributed across its range. The natural breaks, or Jenks classification method, utilizes an algorithm to group values in classes that are separated by distinct breakpoints. This method is best used with data that is unevenly distributed but not skewed toward either end of the distribution. The standard deviation classification method forms each class by adding and subtracting the standard deviation from the mean of the dataset. This method is best suited to be used with data that conforms to a normal distribution. Other data classification methodologies include equal area and optimal. Section 603, Understanding of Analytical Operations and Methods. The overlay analysis methodology, based on Boolean logic, includes: first, define the problem. Second, break the problem into submodels. Third, determine significant layers. or create layers as necessary. Fourth, reclassify or transform data within a layer. A spatial overlay is the process of superimposing layers of geographic data that cover the same area to study the relationship between them. Overlay is the process of taking two or more maps or layers and superimposing them for showing relationships between the features. Vector overlay tools include identity, intersect, symmetrical difference, union, and update. Vector overlay tools explained are: identity is taking input features and splitting them by overlay features. Intersect is selecting only features common to all input layers. Symmetrical difference is selecting features in common to either the input layer or the overlay layer, but not both. Union selection is selecting all input features. Update overlay is inputting feature geometry replaced by an update layer. Raster overlay tools include zonal statistics. Zonal statistics summarizes values in a raster layer by zones or categories in another layer. For example, calculate the mean elevation for each vegetation category. Combine assigns a value to each cell in the output layer based on unique combinations of values from several input layers. Single output map algebra overlay lets you combine multiple raster layers using an expression you enter. For example, you can add several ranked layers to create an overall ranking. Weighted overlay automates the raster overlay process and lets you assign weights to each layer before adding. You can also specify equal influence to create an unweighted overlay. Weighted sum overlays several rasters, multiplying each by their given weight and summing them together. Understanding overlay analysis. Overlay analysis is a group of methodologies applied in optimal site selection or suitability modeling. It is a technique for applying a common scale of values to diverse and dissimilar inputs to create an integrated analysis. Suitability models identify the best or most preferred locations for a specific phenomenon. Overlay analysis often requires the analysis of many different factors. For instance, choosing the site for a new housing development means assessing such things as land cost, proximity to existing services, slope, and flood frequency. This information exists in different rasters with different value scales: dollars, distances, degrees, and so on. You cannot add a raster of land cost, dollars, to a raster of distance to utilities, meters, and obtain a meaningful result. Additionally, the factors in your analysis may not be equally important. Even with a single raster, you must prioritize values. These are the general steps to perform an overlay analysis. 1. Define the problem. 2. Break the problem into submodels. 3. Determine significant layers. 4. Reclassify or transform the data within a layer. 5. Weight the input layers. 6. Add or combine the layers. 7. Analyze. Once again, the general steps to perform an overlay analysis are: 1. Define the problem. 2. Break the problem into submodels. 3. Determine significant layers. 4. Reclassify or transform the data within a layer. 5. Weight the input layers. 6. Add or combine layers. 7. Analyze. How fuzzy membership works. The fuzzy membership tool reclassifies or transforms the input data to a 0 to 1 scale based on the possibility of being a member of a specified set. 0 is assigned to those locations that are definitely not a member of the specified set. 1 is assigned to those values that are definitely a member of the specified set. And the entire range of possibilities between 0 and 1 are assigned to some level of possible membership. The larger the number, the greater the possibility. The input values can be transformed by any number of functions and operators available in the ArcGIS Spatial Analyst extension that can reclassify the values to the 0 to 1 possibility scale. However, the fuzzy membership tool allows you to transform continuous input data based on a series of specific functions that are common to the fuzzification process. How fuzzy overlay works. The fuzzy overlay tool allows the analysis of the possibility of a phenomenon belonging to multiple sets in a multi-criteria overlay analysis. Not only does fuzzy overlay determine what sets the phenomenon is possibly a member of, it also analyzes the relationships between the membership of the multiple sets. Overlay type lists the methods available to combine the data based on set theory analysis. Each method allows the exploration of the membership of each cell belonging to various input criteria. The available methods are fuzzy and, fuzzy or, fuzzy product, fuzzy sum, and fuzzy gamma. Each approach provides a different aspect of each cell's membership to the multiple input criteria. Fuzzy and. The fuzzy and overlay type will return the minimum value of the sets the cell location belongs to. The fuzzy or overlay type will return the maximum value of the sets the cell location belongs to. The fuzzy product overlay type will, for each cell, multiply each of the fuzzy values for all the input criteria. The fuzzy sum overlay type will add the fuzzy values of each set the cell location belongs to. The fuzzy gamma type is an algebraic product of fuzzy product and fuzzy sum, which are both raised to the power of gamma. Section 604, Knowledge of Map Algebra. Map algebra are the various functions performed on cells based on neighboring cells for raster datasets. Local operations combine rasters that overlay each other. They add, subtract, etc. the cells that are in the same location. Global operations apply a formula to all cells. They add, subtract, multiply, etc., all cells based on one value. They can find the distance from one cell to all cells. Focal operations calculates a value based on all neighboring cells. Focal operations can find the average of all the cells around a certain cell. The zonal operations compute a value based on cells in a particular zone, such as a watershed. Map algebra types of operations include local operations, global operations, focal operations, and zonal operations. Map algebra is an algebra for manipulating geographic data, primarily fields. It was developed by Dr. Dana Tomlin and others in the late 1970s. It is a set of primitive operations in a geographic information system which allows one or more raster types of similar dimensions to produce a new raster layer using mathematical or other operations such as addition, subtraction, etc. Map algebra is raster math. Map algebra basically involves doing math with maps. But the key difference is that it only applies to raster data. That's why we also call it raster math. Types of map algebra. The most common type of map algebra is a cell-by-cell function. This type has rasters directly stacked on top of one another. Then the function applies to cells aligned with each other. But you can also change the configuration so it's not only cell by cell. Types of map algebra operations include local, focal, zonal, and global. Local operations use map algebra on a cell-by-cell basis. You can have two rasters stacked on top of each other and then add each corresponding cell one by one. Global operations. Global operations apply a bulk change to all cells in a raster. If you want to add a value of 1 to all grid cells, this is a global operation. Focal operations. Focal operations are spatial functions that compute an output value of each cell using neighborhood values. For example, convolution, kernel, and moving windows are focal operations. A moving window. A moving window is a rectangular arrangement of cells that shifts in position. Applying an operation to each cell from a moving window smooths values in a raster. Zonal operation. Zonal operations apply a math function to a group of cells within a specified zone. A zone could be a vector or raster format. Mathematical functions. Here are examples of operations that you can use for map algebra. Arithmetic operations include addition, subtraction, multiplication, and division. Statistical operations include minimum, maximum, average, and median. Relational operations include greater than, smaller than, and equal to. Trigonometric operations include sine, cosine, tangent, and arcsine. Exponential and logarithmic operations include exponent and logarithm. Section 605, Knowledge of Descriptive and Spatial Statistics. Descriptive statistics is the discipline of quantitatively describing the main features of a collection of information. Descriptive statistics summarizes a sample to learn about the population. Summary statistics is used to summarize a set of observations. Coefficient of determination uses R squared, a number that indicates how well data fit in a statistical model. R squared summarizes the population's fit to a line or a curve. 1 indicates the line fits perfectly with the data. 0 indicates the line does not fit at all, and that the data is random. Descriptive statistics. A descriptive statistic is a summary statistic that quantitatively describes or summarizes features from a collection of information. Descriptive statistics is distinguished from inferential statistics or inductive statistics by its aim to summarize a sample rather than use the data to learn about the population that the sample of data is thought to represent. This generally means that descriptive statistics, unlike inferential statistics, is not developed on the basis of probability theory and are frequently non-parametric statistics. Non-parametric statistics is the type of statistics that is not restricted by assumptions concerning the nature of the population from which a sample is drawn. This is opposed to parametric statistics, for which a problem is restricted by assumptions concerning the specific distribution of the population. Some measures that are commonly used to describe a data set are measures of central tendency and measures of variability or dispersion. Measures of central tendency include the mean, median, and mode, while measures of variability include the standard deviation or variance. The minimum and maximum values of the variables, kurtosis, and skewness. Central tendency is a central or typical value for a probability distribution. Dispersion is the extent to which a distribution is stretched or squeezed. Common examples of measures of statistical dispersion are the variance, standard deviation, and interquartile range. For instance, when the variance of data in a set is large, the data is widely scattered. The standard deviation is a measure of the amount of variation or dispersion of a set of values. A low standard deviation indicates that the values tend to be close to the mean of the set, while a high standard deviation indicates that the values are spread out over a wider range. The variance is the squared deviation from the mean of a random variable. The variance is also often defined as the square of the standard deviation. Variance is a measure of dispersion, meaning it is a measure of how far a set of numbers is spread out from the mean. Kurtosis is a measure of the tailedness of the probability distribution of a real valued random variable. Like skewness, kurtosis describes a particular aspect of a probability distribution. Skewness is a measure of the asymmetry of the probability distribution of a real valued random variable about its mean. The skewness value can be positive, 0, negative, or undefined. Univariate analysis. Univariate analysis involves describing the distribution of a single variable. Characteristics of a variable's distribution may be depicted in graphical or tabular format, including histograms and stem and leaf display. Bivariate and multivariate analysis. When a sample consists of more than one variable, descriptive statistics may be used to describe the relationship between pairs of variables. Descriptive statistics include cross-tabulations and contingency tables, graphical representation via scatter plots, quantitative measures of dependence, and descriptions of conditional distributions. A contingency table. A contingency table, also known as a cross-tabulation or crosstab, is a type of table in a matrix format that displays the multivariate frequency distribution of the variables. A scatter plot is a type of plot or mathematical diagram using Cartesian coordinates to display values for typically two variables for a set of data. The data are displayed as a collection of points, each having the value of one variable determining the position on the horizontal axis and the value of the other variable determining the position on the vertical axis. Correlation or dependence is any statistical relationship, whether causal or not, between two random variables or bivariate data. A correlation may indicate any type of association. It usually refers to the degree with which a pair of variables are linearly related. An example of correlation or dependence is between the height of parents and their offspring. Another example of correlation is between the price of a good and the quantity the consumers are willing to purchase, which is known as a demand curve. Conditional probability distribution. Given two jointly distributed random variables, the conditional probability distribution of x given y is the probability distribution of x when y is known to be a particular value. The main reason for differentiating univariate and bivariate analysis is that bivariate analysis is not only a simple descriptive analysis, but also it describes the relationship between two different variables. Quantitative measures of dependence include correlation, such as Pearson's R when both variables are continuous, or Spearman's ρ if one or both are not, and covariance, which reflects the scale variables are measured on. The slope in regression analysis also reflects the relationship between variables. The unstandardized slope indicates the unit change in the criterion variable for a 1-unit change in the predictor. The standardized slope indicates this change in standardized or z-score units. Highly skewed data are often transformed by taking logarithms. The use of logarithms makes graphs more symmetrical and look more similar to the normal distribution, making them easier to interpret intuitively. Pearson correlation coefficient. The Pearson correlation coefficient, or Pearson's R, is a correlation coefficient that measures linear correlation between two sets of data. It is the ratio between the covariance of two variables and the product of their standard deviations. Thus, it is essentially a normalized measurement of covariance, such that the result will always be between -1 and 1. Spearman's rank correlation coefficient, or Spearman's P, is a nonparametric measure of rank correlation, or statistical dependence between the rankings of two variables. It assesses how well the relationship between two variables can be described using a monotonic function. A perfect Spearman correlation of +1 or -1 occurs when each of the variables is a perfect monotone function of the other. Covariance is a measure of the joint variability of two random variables. If the greater values of one variable mainly correspond with greater values of the other variable, and the same holds for the lesser values, the covariance is positive. In the opposite case, when the greater values of one variable mainly correspond to lesser values of the other, the covariance is negative. The sign of covariance, therefore, shows the tendency in linear relationship between the variables. The predictor. A prediction is a statement about a future event or data. The z-score. The z-score, or standard score, is the number of standard deviations by which the value of a raw score is above or below the mean value of what is being observed or measured. Raw scores above the mean have positive standard scores, while those below the mean have negative standard scores. It is calculated by subtracting the population mean from an individual raw score and then dividing the difference by the population standard deviation. This process of converting a raw score into a standard score is called standardizing or normalizing. Normal distribution. A normal distribution, or Gaussian distribution, is a type of continuous probability distribution for a real-valued random variable. Coefficient of determination. The coefficient of determination, denoted r squared and pronounced r squared, is the proportion of the variation of the dependent variable that is predictable from the independent variables. A simple linear regression is a linear regression model with a single explanatory variable. That is, it concerns two-dimensional sample points with one independent variable and one dependent variable, and finds a linear function, a non-vertical straight line, as accurately that as accurately as possible predicts the dependent variable. The Pearson correlation coefficient. The Pearson correlation coefficient is a correlation coefficient that measures linear correlation between two sets of data. It is the ratio between the covariance of two variables and the product of their standard deviations. Thus, it is essentially a normalized measurement of the covariance such that the result always has a value between -1 and 1.